Alright, so 18 and then 3. So 18. So 18. Two balls of clay are thrown each other in such a way that once they hit, they stick together. So what type of collision is that? Totally inelastic. Totally inelastic. The first ball is this mass. It's moving in this direction as measured counterclockwise from the x positive axis. Second ball is this. It's moving at the speed of this in the direction of this. It's measured clockwise from the x positive axis. Ooh, careful there. Clockwise and counterclockwise. Once the balls join together, they move in the x positive direction. Alright? What is the speed of the first ball? Oh, okay. So, let's see. I know that momentum is conserved in the collision. Right? And now I need to do my before, during, and after. My during is actually not going to have much. Let's put a, I don't know, we'll put a boom there. And I know beforehand, to do them in red and green. Let's see. So, first one I'm going to do in blue. The first ball, this is moving 16.4 degrees as measured counterclockwise from the x-axis. So that would mean, let's see, x-axis is to the right, 16.4, so that's the momentum ball one has beforehand, right? And I can even, do this and go, oh, that's 16.4 degrees. And then ball number 2, 45.5 degrees measured clockwise from the x-positive axis. So that would be kind of down like this. So that's momentum 2. Right? And then afterwards, they tell me they stick together so they become a new thing. So I'm going to do that in red, and it moves directly this way. So that's the momentum of this new object, which I'll call 12. All right? So that's what I should have had. You should have had for your Y. Some words, and then before, during. In this case, since we're not looking at impulse, I'm not going to do much during, and then afterwards. Questions on the Y? No. Alrighty. So in my how, from my equation sheet, I can go and look up that momentum is inertia times velocity. Right? That I pull down from Unit 1, maybe. And since I know that this is conserved, I know that my blue momentum plus my green momentum if I add those two together, I get my momentum in that direction. Now, mine kind of looks like a right triangle, but I know it's not a right triangle. So I have to make a choice now. Do I want to just deal with it as a triangle, and I know I'll have to use some of those scary trig stuff of law of sines and law of cosines, but I'm pretty confident there'll be less math steps. Or do I want to break these into their components and say, okay, I know that the components of blue plus the components of green will equal the components of red. I can do it either way. Anybody have a preference? Or somebody please have a preference so we can move forward. Components. Okay. I was hoping for less math. All right, that's fine. We'll do components. So let's see. Blue would have a component in this direction and a component in that direction. And this would be whatever I drew up here. 16.4. And green is going to have a component in this direction and a component in that direction. And this angle is going to be 45.5 degrees. Using a little bit of my geometric knowledge. Oh, look, their y components are going to cancel each other out. Cool. And their x components are going to add together to be the magnitude of the momentum of the two together. D12. So now it'd be good to, what did they actually ask me to find? What is the speed of the first ball before the collision? What is the speed of the combined after the collision? All right. So, if I want to know this, I'm going to use that fact that these two, that the y components are equal to see if I can find the speed of the first ball before. And then I can add up the other two to find the speed of the combined afterwards. So let's do part A. So I know, let's see, I'll write my equation that momentum of 1 in the x direction plus momentum of 2 in the, oops, not x, y direction, might make that a y, equals 0. How do I know that they add up to 0? How do I know that, though? Well, visually, yep, I set that up nicely. But what do they tell me about the final momentum? I heard it's conserved. Pat, what did you say? Okay. They tell me something else, though. Once the clay balls join together, they move in the x positive direction. If they move in the x positive direction, how much vertical momentum do they have? 0. That's where I got that 0 from. And so I know that so I'm going to end up with P1x, notice I've dropped my vector symbol, equals y equals P2y. Oh, I'm going to do those again in color. Just make it pretty. P1y equals P2y. Isn't that pretty? And let's see, so P1y would be P1 opposite, so sine 16.4 degrees. That would equal P2, which would be P2 sine 45.5 degrees. Right? And P1 would be mass of 1, speed of 1, mass of 2, speed of 2, do I know the mass of the first blob of clay? Yes. Do I know the speed of the first blob of clay? No. Do I know the mass of the second blob of clay? Yes. Do I know the speed of the second blob of clay? Excellent. So I know enough to plug in everything I know, and then to find the speed in meters per second of the first blob of clay, which is ironically what they asked me for in A. Not ironically. Should we talk about part B? All right, let's talk about part B. In part B, we're using the same idea, except we have the momentum of 1 in the x plus momentum of 2 in the x equals the momentum of 12 in the x, which is only the whole momentum of 12. So this one would be P1 cosine 16.4 degrees plus P2 cosine 45.5 degrees equals P12. And then you just substitute in. What's going to be the mass of our new object that's object 1, 2? How are you going to figure out how much mass it has? Add the two masses together, right? Yeah. Mass 1 plus mass 2, speed of 1, 2. We'll work backwards this time. Mass of 2, speed of 2, cosine of 45.5, plus mass of 1, speed of 1, cosine of 16.4. You know everything except the speed of 12. So plug it and you got it. All right, so on to number 3, which is one of those that it's a relative motion actually problem. You've got this robin flying due north with the speed of this. So they're telling you, and they say relative to the air. So they're telling you that's the velocity of the robin relative to the air. The air moves east with this speed, and that's relative to the ground. So they've told you now the robin relative to the air, and the air relative to the ground, and now they want the robin speed relative to the ground. So you've got 3 frames of reference going on here. The robin, the air, and the ground. So we're going to relate those. And that's why it's a traditional lie, but I think you should include a diagram with it. So you want to start off with your good old everyday facts that like all motion is relative. And by that we mean based on your frame of reference. All right. Now, I always like to include a diagram with this. So I've got, let's see, we'll use red for our robin. So our robin is flying north. That's the velocity of the robin with respect to the air. The air moves east. So we've got the air. I'm going to use blue for the air. That's the velocity of the air with respect to the ground. And if I think about it, I think my robin is going to move this way. That would be the velocity of the robin with respect to the ground. So just kind of a little diagram to kind of get my head thinking. The robin's trying to go north, but it's going north compared to the air, and the air is moving east. So I think my guess is that that's going to be that way. Yep. All right. So, physics equations that I would need for this one. I'd go back to my equation sheet and look up relative motion, I think, which is written this way: the velocity of A with respect to B plus the velocity of B with respect to C equals the velocity of A with respect to C. Right? And for me, the way I keep that straight in my mind is I'm saying that the velocity of the robin with respect to the air plus the velocity of the air with respect to the ground has to equal the velocity of the robin with respect to the ground. Remember, the insides have to agree subscript-wise, and I end up with the outsides. So that's kind of mathematically how I'd write it. Vectorially, I'm going to draw myself a picture to help me remember it. This is what that equation is saying, but drawing it instead, I add those two together, I end up with this one. Well, the question is, did you use that equation correctly? Because this doesn't say this number plus this number equals this number. It says this vector plus this vector. And when I see how they're arranged, I realize they're in a triangle. And it happens to be a right triangle. So if I want to figure out, see, what do they ask me? What's the speed, right? Yep. So that's going to be the magnitude of the green vector here. And to find the magnitude of the green vector in a right triangle, that's why it's called the hypotenuse. So I have to use my friend Pythagoras' ideas, which says that the magnitude of the robin to the air is, so there's speed plus the speed of the air with the ground equals the speed of the robin to the ground squared. And that would be my answer in meters per second. Remember, that's one of the consequences of going into two dimensions. You can't just, positive and negative are not descriptive enough to describe direction anymore. You need to use that geometric and trigonometric knowledge you've gained in your math courses over the years.